Welcome back, and this is part 2 of the area under a curve, part of integral calculus. If you haven't seen part 1, click the tab above or look at the link in the description. I strongly advise you to do that before we go over these. In these 3 examples though, they're slightly different to part 1, where the area appears below the x-axis, and in some cases they're asking you to find the area bound between the curve and the x-axis, and that involves a positive and negative and just what to do in that instance. So there's 3 slightly different questions here. Let's dive in. Okay, so here's the first question, and it is to do with a quadratic equation. First of all, they ask us to find the points A and B, those are the intercepts, and then find the area beneath the curve between those 2 points. So this is a mixture of a functions question and a integral calculus question. So what I'll do first of all is I will take out a factor of -1 and be very careful here. That will now turn to -x and -6. The reason I'm doing that is then I find it easier to factorize this, because this will be -1, this will become x minus 3, and this will become x plus 2. And there we go, I factorized it. So now I can go ahead and find out when the curve will be equal to 0. So I can equate that to 0 on the left there. I can see that will be when the brackets are, this value has to be 3, or this value here has to be -2. So I'm just going to transfer those results over to my diagram. So we have -2, that's going to be A, and our value B will be 3. All right, so that's going to be the limits on our integral sign in just a moment. So it says, hence find the shaded area. So therefore we will set, so I'll just label this as B now, and this is A. So we want to find the area is the integral between the lower limit, and in this instance that's going to be -2 to 3 of our function, and that's going to be we can just use the original function. We don't need to use the factored version, and we're going to be using power rule when we do this. So we're going to be adding 1 to the power and dividing by the new power. So we'll get -x cubed over 3 plus x squared over 2 plus 6x, and that's all going to be in these square brackets, like these integral brackets, and we need to put our limits on 3 and -2 as it's a definite integral. Now we just need to go ahead and substitute those in. So I'm going to get -3 cubed, so that's -27 over 3. We'll deal with all of that in a moment. We're still in the stage where we're plugging 3 into all of this. So we're going to get 3 squared, which is 9 over 2, and then plus 3 times 6, 18. Right, that's all in the first bracket. And now we have subtract, and now we got to plug -2 into all this. So -2 cubed is a -8, but then it's times minus, so that's going to be 8 over 3. And then we've got -2 squared, which is 4. 4 divided by 2 is 2, so that's plus 2. And -12, right? Okay, so, and I'll just go ahead and tidy all this up for you. So -27 over 3. Plus 11 over 6, which is 125 over 6 units squared is the area. So 125 over 6 units squared. Okay, so that is the end of that first question. Okay, so on to question 2. So this is an interesting one, because we are going to get an area that's negative. As we can see from this diagram, this is 0, 0, and this is 2, 0. So therefore then, if you were just to simply compute on a calculator the integral of 0 to 2 of this function, which is e to the -x minus 1 with respect to dx, you will get a negative area. Right, now the issue here is we don't want to get a negative area, because we want to find the shaded area bound between the function and the axis, and area is a scalar value, so we don't want to get a negative value. So there's a very simple fix for that. Okay, what you can do is, if you find an area that's negative, there's either this, you can either do the absolute value of that area at the end. Therefore then, let's say for example the area came out to be -4, then you can do the absolute value of that, and that would become 4. right? So positive. So it seems like a simple fix. When it's an expression like this, it's sometimes a little bit more difficult if you have to do it by hand or without a calculator. So what you can do is you can do the absolute value at the very, very beginning, right? Because in doing so, what you can do is you can replace that expression then with if you have the absolute value of x and you knew that that value of x was going to be negative, you can just replace that with -1 times that value of x. Because now, whatever that value is in there that comes out to be negative, when we multiply it by -1, we would end up with a positive value, right? So in this question here, if you kind of know or can see immediately that it's going to come out to be negative, you can just make that switch at the very, very beginning. So that's exactly what I'm going to do here. I'm going to say that the area of this region is still between 0 and 2, but I'm going to have -1 times by e to the minus x minus 1 dx. Now, what I can do straight away is I can just times that out and tidy that up before I even start. So 0 to 2 of, now, -1 times -1 will be +1 minus e to the minus x. So that's like all done before I've even started doing any integration here. Now I'm going to integrate this as I normally would do, and that would become x. This would become minus e to the minus x, but divided by the derivative of the power. Now, the derivative of the power is -1, so you divide by -1. That's all going to become positive, right? And the limits on this integral, this definite integral, are going to be 2 and 0. So if I just go ahead and substitute those values in now, we're going to get 2 plus e to the minus 2, and then we plug 0 into this, right, will be a second. So it's subtract. Now 0 into x is going to be 0. We've got to be a little bit careful here because 0 into this will be e to the 0, but that's actually just 1. So now in the final line down, we're going to get 2, right, plus e to the minus 2, subtract 0, that doesn't matter, but subtract this expression, which is 1, right? So all of this is going to come out to be 1 plus e to the minus 2 if you had to write it as an exact value. Now, that is units squared. So that's something we didn't see in part 1, and that is a little bit more tricky. Okay, on to our final example here. Find the area enclosed by the function x cubed minus 9x and the x-axis. So over here, what they want us to do is they want us to find where like the area is sort of sectioned off, and that will be between these intercepts here, 1, 2, and 3. And then there'll be another enclosure over here. We won't count anything to the right or left because we can see that the function tends to positive infinity and negative infinity. So there'll be no enclosures left. So it's basically where is the area sort of like sectioned off. So we just got to find those intercepts if we can't easily see them from the graph, and that's easily done. That's a function style problem. So we can just factor out an x and say x squared minus 9, and that looks like that's a difference of 2 squares. So we've got x minus 3 and x plus 3. So those intercepts are going to be at 0, 3, and -3, right? Based on what creates 0 for f of x. So 0, 3, and -3. So we're just going to go ahead and put those on now. So this is going to be the -3, this is going to be the 0, and this is going to be the 3. Now those will determine what types of limits I have on my definite integral. Now the good news here is because of its sort of asymmetrical type nature, it's like almost like a reflection in the x-axis and then in the y-axis. These areas are going to be exactly the same. But if it wasn't, then we would have to do what we did on the previous example and deal with this area here on the right, because we can see that it's negative. If we were to deal with that area, 0 to 3, we would know that that would be negative. So we'd have to make that correction that we did on the previous example of putting the modulus round the result and then working with it. But actually I could see straight away that this is going to be exactly the same value. So that's kind of good news. What we're going to do is we're just going to find the area of the first positive region, okay? And so that will mean that that is the area between -3 to 0, and the function was x cubed, let's just write that down, x cubed minus 9x with respect to dx. Okay, so that will give us x to the 4 over 4 minus 9x squared over 2. Put our integral brackets in, and our limits 0 to minus 3. Now we just go ahead and substitute these limits in now. So we're going to get, well, when we plug 0, and this is going to be 0, and this second term will be 0, minus, now let's just plug in minus 3. So minus 3 to the power 4 is 9 times 9 is 81 over 4, minus, that will also be 9 times, that will also be 81, but this time over 2. Right, so we've just got to tidy that up. We've got 81 over 4 units squared, right? So that is the area. Let's just go back over to that. That is the area here that I circled in red, which is 81 over 4. Now, I said through inspection, I can see because this is 3 and this is 3 and it goes through 0, that this area is going to be exactly the same. So I can double that area. Now, if you didn't, you'd have to do this all over again, but with the absolute value around that, and just look back at example 2 to see how I did that. So I'm just going to, in the essence of time, just double this then. So this time I will get 2 times 81 over 4, and that will give me 81 over 2, and I can't really go any further there, right? So that's units squared. So that will be the entire area of the enclosure in this question. Let me know how you get on in the comments below. Don't forget to like and subscribe to the channel. See you next time.